Okay, can I have everyone's attention, please? Let's go ahead and start. So, any questions before I begin? So, if you guys remember, we stopped last time at the point where we were looking at polyprotic acids. And polyprotic acids are those acids that have more than one dissociable proton. All right? And we said that when you have more than one dissociable protons, then the protons come off sequentially, and we call these competing equilibria. All right, so we took the example of carbonic acid last time, and if you guys remember, carbonic acid has two acidic protons. So it's got two dissociable protons, and we said that when they come off in the first step, we have the first proton coming off, so that now you have hydronium ion and this anion being formed. And then the second step, the second proton comes off, and you see that happening. Okay, so we said we look at when we have sequentially protons coming off, then we have more than one acid dissociation constant. So you have Ka1 and Ka2. And we said when you, in the case of polyprotic acids, Ka1 is always larger than Ka2. And if you have a Ka3, in this case you don't, but if you have a Ka3, then Ka2 will be greater than Ka3, and so on and so forth. All right? And because of the magnitude of the first acid dissociation constant and the second acid dissociation constant, we can make some estimates about the relative concentrations of all the species in solution. All right? And we said, if you take the first step, in the first step we said Ka1 is 10 to the negative 7. So that means the first step, it's a weak acid. All right? H2CO3 is a weak acid. And because Ka is so small, what does that tell us about that equilibrium composition? Is it going to be towards reactants, or is it going to be towards products? Reactants. Can everybody see that? Because it's 10 to the negative 7. So that means for the first equilibrium, almost, so these are approximate numbers, but you can say almost 99.99% is this, and only a very small 0.01% perhaps is on this side. Does that make sense? At equilibrium. So that's the composition that you would establish from the first one. Now if you move on to the second equilibrium, now what happens is for the second equilibrium, Ka2 is 10 to the negative 11th. So the second equilibrium is also a weak acid, and its equilibrium is also going to lie on the reactant side. So if you have 0.01% that you start off here, now you have 0.01% on this side, but all of this will lie on this side. Can everybody see that? So that means this will remain approximately 0.01%, and only very small amount of carbonate anion, CO3 2- will be there in the equilibrium mixture. So if we want to kind of estimate the relative magnitudes of the concentration, we know in this mixture, the major species is going to be that, because that's going to be there in the largest amount. Then we would call this the minor species. It's going to be there in lesser amount. And then, for a lack of any word, we're going to say this amount is so small, we're going to say it's minuscule. Okay? And that's because it's going to be there in lesser amount than even the minor species. All right? So now we set about to calculate this. And so at the end of class last time, we went through an example of a polyprotic problem. And if you guys remember, we said, so I'm just going to quickly go through the calculation because we kind of rushed through it at the end of class last time. So we were asked to calculate of all the species that are there if you have a 0.034 molar concentration of carbonic acid. So if you guys remember, we started with the first equilibrium. We said you deal with this in the sequence. All right? And so we're going to start by looking at the first equilibrium. And if we just look at the first equilibrium, then we can say that we started with the initial amounts of 0.034, and then we had To begin with, no hydronium ion and no HCO3 minus. All right? And then at equilibrium, we can set up the expressions. And we know at equilibrium, this is going to be 0.034 minus x, x. You can put it in the equilibrium expression and make the approximations because this Ka is 10 to the negative 7. And you can figure out what x is. And x comes out to be 1.2 times 10 to the negative 4 molar. And then we validate our approximations. And you know, when we check validation, we know it's well below our 5% threshold. So if we're looking at the concentrations that come from the first step, we know that H2CO3 would be 0.034 minus x. This x is so small compared to 0.034 that within the range of significant figures that we're looking at, you can see it hardly changes the concentration of the initial, the concentration of H2CO3. So we end up with 0.034. Hydronium ion concentration will be 1.2 times 10 to the negative 4 because that would be x. And then HCO3 minus would be 1.2 times 10 to the negative 4 as well. Now this is what we usually did if we had just one deprotonation taking place, and we would stop at that point. All right? But now we have a second step where we have now another competing equilibrium where now the second proton comes off. All right? So we want to look at the deprotonation of the second proton. Then for the second step now, we write the appropriate equilibrium, and we know that Ka2 is 4.8 times 10 to the negative 11. Now for the second step, because the second step relies on the products formed in the first step, if you take the second step, our initial concentration of HCO3 minus will be the concentration of HCO3 minus that comes from the first step. That's what we calculated. That was the x in the first step. Do you see that? So now this would be the initial concentration of HCO3 minus. We're not concerned about the concentration of water. But over here, we do have hydronium ion as well, because in the first step, you're forming hydronium ion as well. So the hydronium ion that comes in the first step would be the initial concentration of the hydronium ion in the second step. All right? And of course, we have none of this. So now we're going to let the reaction, because we have only 0 carbonate, you know that this reaction has to proceed in the forward direction. And if it's proceeding in the forward direction, then the relative change for the second step, and just so that you don't get confused with x, we're going to use a different value y. So now for this would be negative y plus y plus y. So then at equilibrium, we can say you have 1.2 times 10 to the negative 4 minus y. This would be 1.2 times 10 to the negative 4 plus y and y. All right? And so now we can look at the equilibrium expression for the second step, which is Ka2, which is 4.8 times 10 to the negative 11. That equals the hydronium ion concentration times the carbonate ion concentration divided by the HCO3 minus concentration. All right? And this would be 1.2 times 10 to the negative 4 plus y times y divided by 1.2 times 10 to the negative 4 minus y. So now again, to keep the math simple, we got to ask ourselves, can we make an approximation? And if you look at the K value, the Ka2 is 10 to the negative 11. That's an extremely small number. All right? That means if the reaction is proceeding in the forward direction, it's only going to react to a very, very small extent. All right? And therefore, that y has to be extremely small. All right? So what we do is we make the approximation. And so we say this 1.2 times 10 to the negative 4 plus y would equal that, and minus y would equal that. So what we're saying is y is so small, we're going to neglect it. All right? So we put that back in this equation. Now you can see they cancel out. And therefore, y comes out to be 4.8 times 10 to the negative 11. All right? And at this point, you would have to check validity. So if you check validity, we said that that comes out to be 4 times 10 to the negative 5%. So if you take this number divide by 1.2 times 10 to the negative 11 times 100. So you can see that that falls way below our threshold. Okay, that number is so small that we can actually neglect it. Got it? So now we can go back and say that we know what Y is, and the carbonate ion concentration is Y, so this equals Y, and that comes out to be 4.8 times 10 to the negative 11 molar. Now what you'll notice is that very often when you look at the second proton coming off, that concentration of carbonate will actually equal Ka2, because those two values, the hydronium ion concentration and the bicarbonate, which is the HCO3 minus concentration, will cancel each other out. So in all cases, you'll find that it actually equals the Ka2 value. All right? So now in conclusion, let's put all the concentrations. So we said that H2CO3 is, we already calculated that in the first step, and the H2CO3 concentration that comes from the first step is 0.034 molar. All right? Now, the next one is HCO3 minus. Now, the HCO3 minus comes from two steps. All right? It comes from the first step as well as the second step. And in the second step, we know that the HCO3 minus is 1.2 times 10 to the negative 4 minus Y, which is 1.2 times 10 to the negative 4 minus 4.8 times 10 to the negative 11. Can you see this number is so small compared to this that the concentration is 1.2 times 10 to the negative 4 molar. In other words, the concentration of HCO3 minus comes primarily from the dissociation of the first step. Okay? And then if you take the hydronium ion concentration is 1.2 times 10 to the negative 4 plus Y, which is 1.2 times 10 to the negative 4 plus 4.8 times 10 to the negative 11, which once again is 1.2 times 10 to the negative 4 molar. And then lastly, we look at the carbonate ion concentration, and we know that the carbonate ion concentration equals the concentration of Y, which is 4.8 times 10 to the negative 11 molar. So what we've done is we've calculated the concentrations of all of the species in that solution. And if we want to rank these concentrations, can you see that if the concentrations that I calculated, if I want to rank them, this would be H2CO3. That's much larger. The concentration of that is much larger than HCO3 minus. All right? And HCO3 minus and H3O plus are the same. All right? And then this will be much larger than the carbonate ion concentration. And remember, that was what we started off with. That was sort of, if you compare it to the assumption that we made at the beginning, just based on the equilibrium constant, you can see that these concentrations that we calculated fall within that same range as well. Now finally, if they ask you to calculate the pH of this solution, then we know that the hydronium ion concentration equals 1.2 times 10 to the negative 4 molar. Therefore, pH would be the negative log of that. And if you take the negative log of that number, let's see what you end up with, you get 3.92. All right, so if you're going to calculate, once you calculate what the hydronium ion concentration is, now you can figure out what the pH of that solution is. Now remember, this is an acid, so does our pH come out to be acidic? Yes, so we know that our calculations are on the right track. All right? So now if you notice, you guys are carrying out homework, all right? And some of the themes that are being developed here is, and you should have a checklist about some skills that you've mastered. All right? And one of the skills is that I will be checking when I test you is, can you calculate the pH of a weak acid? All right? Can you calculate the pH of a strong acid? All right? Can you calculate the pH of a strong base? Can you calculate the pH of a weak base? All right? Can you calculate the pH of a polyprotic acid? All right? So those are skills. And if you look at the online homework, you'll see that if you take a weak acid, they'll give you the concentrations you start with, initial concentration, and ask you to calculate pH. All right? Or they'll give you the pH of the solution and the equilibrium constant and ask you to calculate the initial concentration. Or they'll give you the pH of the solution and give you the initial concentration and ask you to calculate Ka. Do you see that? So it's the same thing. Either you're working in two different directions, but those are the skills that you need to master. Now there's one unit that you'll see coming up, and I don't want you to get thrown off, and that's the homework that's due tomorrow that talks about hydrolysis. All right? Now, we use the word hydrolysis whenever water is split. All right? So hydrolysis is a generic term. All right? So if you use the word hydrolysis, it starts with hydro. Hydro means what? Water. Lysis means what? To break up. All right? In all of these acid-base dissociations, can everybody see we're breaking up water? All right? When it's basic, you're breaking up water to give you OH minus. All right? If it's acidic, you're breaking up water so you get H plus that clings to another water and gives you H3O plus. Do you see that? So when you say the word hydrolysis, don't get thrown off. It's the same thing as Ka and Kb. Do you understand that? All right? So it's just that they're rephrasing in a different way so that you just get comfortable looking at this from different angles. So if you look at that unit on hydrolysis, it's the same thing. They give you, instead of giving you Ka, they say the hydrolysis for the equilibrium. All right? So instead of saying acid dissociation constant, they say hydrolysis. All right? Because acid dissociation constant and base dissociation is also hydrolysis, because in both cases you're splitting water. So when they say instead of saying acid dissociation, if they say the hydrolysis of water and give you an equation, you should be able to look at the equation and say, oh, that's Ka. All right? And then they want you to calculate Kb. All right? And you know, what is the relationship between Ka and Kb? Ka times Kb equals Kw. All right? That's all it is. All right? And so just don't get thrown off by the terms they're using, but they just want you to get used to some of those terms, because if you're a bio major and as you go on taking biochemistry and so on, very often they use the word hydrolysis often. And so you should be able to look at that and figure that out as well. Okay? Great. So any questions up to this point? So we've looked at acids, and we said you can have weak acids or strong acids. We've looked at bases. We've looked at the fact that you can have weak bases or strong bases. And then we've looked at polyprotic acids. And just like polyprotic acids, you can have polybasic substances as well. And the same process applies, except that now for those, you'll have Kb1, Kb2. All right? Now we're going to move on to looking at a third topic. And the third topic is acid-based properties of salts. Okay? So now, we've used the word salts before. Can you give me another word for salts? Ionic compounds. All right? So another word for salts are ionic compounds. And all of you know, we've looked at ionic compounds in great detail. You know how to identify ionic compounds. It's got to have a cation and an anion. It has to have a combination of a metal and a nonmetal. All right? And so salts are also called ionic compounds. Now, it turns out salts can be either soluble or insoluble in water. So depending on the type of salt, you can have some salts that are insoluble and some salts that are soluble. All right? And later on, we'll see that the ones that don't dissolve are called insoluble, and we also call them precipitates. All right? So if you take ionic compounds, not all ionic compounds actually dissolve in water. The majority of them do, but there are many that are insoluble. And so in this case, we're going to consider only soluble ones. All right? So in the case of soluble salts, so if we take soluble salts, can act as an acid, base, or be neutral in water. All right, so depending on the salt, so we're going to look at only the ones that dissolve in water. You can have salts that are soluble and insoluble, but if you take the soluble salts, they can act, some salts can act as an acid, some salts can act as a base, and some salts can be neutral. So we're going to look at how do you identify whether it's a solid, whether it's going to be an acid, base, or neutral. Okay? So to look at that, we're going to categorize them into 4 groups. So we'll start with the anions. Okay? So the first is that salts that consist of anions, all right, that are the conjugate bases of strong acids. Okay, salts that consist of anions that are conjugate bases of strong acids are neutral in water. All right? So remember, we're looking at conjugate bases of strong acids. So give me an example of a strong acid. HCl. What is the conjugate base of HCl? Cl minus. Now give me a salt that has Cl minus in it. NaCl. Do you see that? So if you take NaCl now, NaCl is a salt. It's got a cation and an anion. And so NaCl has Cl minus, which is the conjugate base of a strong acid, and these will be neutral in water. So if you put sodium chloride in water, the pH will be 7. Do you see that? And the reason is, do you guys remember, this is the conjugate base of a strong acid. The conjugate base of a strong acids are weak bases. They're so weak that they're weaker than water, and that water is a stronger base. All right, so that's why when you place them in water, they're extremely weak bases. They're so weak in water that if you look at the scale, you'll see that water is a stronger base. Again, if you're not sure, go back to the table that we've been looking at. And remember, these are all strong acids. So these are the strong acids. These are their conjugate bases. So remember, when you look at conjugate bases, the strongest bases are at the bottom. As you go up, the bases get weaker and weaker and weaker. Here, now water comes here, and all of these bases are weaker than water. All right, so water is a stronger base than these. So in water, these can't act as a base because water is a stronger base. Do you guys get that? And therefore in water, it's going to be neutral. All right? And so you can take sodium chloride. We said perchlorate KClO4 aqueous. So this is KClO4. That's a strong, the conjugate base of a strong acid. You can take NaNO3 aqueous, and etc. These are all examples of salts that contain anions that are conjugate bases of strong acids. Now, if you take the second group of anions, salts that consist of anions that are the conjugate bases of weak acids, so we're looking at conjugate bases of weak acids, and we're looking at anions, are basic in water. All right, so now if you take the conjugate bases of weak acids, we said if you have a weak acid, its conjugate base will always be weak. All right, so somebody asked me in discussion, you guys are talking about this, and I had somebody ask me about this. So remember we talked about the fact that these acids are strong. So the conjugate bases of strong acids will be very, very weak bases. Got it? So weak that they can't act as a base in water. Now, if you look at these in this range, these are all weak bases. All right? So the conjugate bases of weak acids will be weak. All right? So if you have a weak acid, when I asked this question to the other class, you know, and I asked them, would the conjugate base of a weak acid be strong or weak? Everybody said, because the acid is weak, that means the base must be strong. Not really. Do you understand that? If the acid is weak, its conjugate base is also weak, because Ka times Kb has to be 10 to the negative 14. So if Ka is 10 to the negative 2, is that a weak acid or a strong acid? 10 to the negative 2. It's a weak acid. All right? So if Ka is 10 to the negative 2 and it's a weak acid, now can you tell me what would the Kb come out for the conjugate base of that weak acid? If it's 10 to the negative 2, what is the corresponding Kb for its conjugate base? 10 to the negative 12. Can you see that? 10 to the negative 12 is also weak. Do you see that? So always, if you have a weak acid, its conjugate base will also be weak. All right? And so that's what we're seeing here. So now we're looking at the conjugate bases of weak acids, and they will act as a base in water. All right? And so if they're acting as a base in water, examples of this would be things like if you have sodium cyanide. Okay? If you have sodium acetate, which is the acetate anion, or if you have, so aqueous, or if you have something like potassium fluoride. These are all conjugate, these all have, so if I wanted to circle these, what we're looking at is the anion. So if I want to circle the anions, you can see these all will be the conjugate bases of weak acids, and therefore they'd act as a base in water. So let's take this. If I take sodium cyanide and put it in water, can everybody see that to begin with, we start with an ionic compound. And we said when an ionic compound dissolves in water, its whole entire lattice structure disintegrates. And so the whole structure falls apart, and we say it dissociates. And when it dissociates, it gives you Na plus Cn minus. So the first step is when you put a salt in water, it breaks apart because salts are crystalline. All right, think about sodium chloride. Sodium chloride is a white crystalline material. The instant you take that salt and put it in water, what happens? It dissolves completely in water. And when it dissolves, it means that the whole structure falls apart. All right, and so you have dissociation taking place. And then after this dissociation is complete, now this is neutral, and this will be basic. All right? And so now, because it's basic, it's the conjugate base of a weak acid, and the reason it's basic is you will establish this equilibrium. In water, it's going to give you HCN aqueous plus OH minus aqueous. All right, where this is the base, this is the acid. For the reverse reaction, this would be the conjugate acid, and this would be the conjugate base. All right, and because this is the conjugate base of the weak acid HCN, this would be Kb, and we know that in tables, usually you get these values as Kas for HCN. So if you know the Ka for HCN, you can put it in that equation and you can figure out what Kb is. All right? And that's a weak base, and so it's going to act as a weak base in water. All right? And can you guys do the same thing at home? So if you take acetate, if you put sodium acetate in water, the first step, it will dissociate to give you the acetate anion and the sodium cation. And then this will act as a weak base in water because you're going to establish that equilibrium. Same thing with F minus. All right? Now, the third is, so up to this point, if you look at these two deal with anions. All right, now let's look at cations. So the third option is, now we're going to look at cations. And so it turns out salts that consist of cations that are the conjugate acids of weak bases are acidic in water. So now we're looking at cations. And when you look at cations, you're looking at the conjugate acid of a weak base. Can you give me an example of a weak base? Ammonia. All right? So ammonia is a weak base. What is the conjugate acid of that weak base? NH4 plus. All right? So if you take NH4 plus in water, now that's going to act as a weak acid. So an example would be NH4Cl. So if you take NH4Cl, now the one that we're interested in looking at is this. All right? So this is the conjugate acid of the weak base NH3. All right? Because it's the conjugate acid of the weak base NH3, you have NH4 plus, and this would be acidic. Now, if I take the anion of this, what is this anion? Cl minus. And what do we know? Is Cl minus acidic or basic? Cl minus is the conjugate base of a strong acid or weak acid? Strong acid. And what do we know about the conjugate bases of strong acids? They are neutral. So it turns out this will be neutral, and that will be acidic. So overall, the solution is going to be acidic. All right? And so why is it acidic? We know that NH4 plus in water will act as a very weak acid to give you H3O plus aqueous plus NH3, where this is the acid, this would be the base. For the reverse reaction, this would be the conjugate acid, and this would be the conjugate base. And this represents Ka, and if ever they give you Kb, for NH3, if you know the Kb for NH3 or Ka for NH4 plus, you can convert one from the other. All right? And because this acts as an acid in solution, this will act as an acid. So can you see, we're taking what we've learned before, but now we're taking it to a high level and we're looking at more complex properties. All right? So now we're looking at salts, and every salt will have a cation and an anion. All right? So now you've got to figure out, you have to look at the cation part of it and ask yourself, is the cation going to act as an acid or a base? Then you have to turn to the anion and you have to ask, will that anion act as an acid or base? All right? Now lastly, okay, cations of group 1 and group 2 metals are always neutral. All right? So if you take metals, and we're looking at group 1 and group 2 metals, and if you turn to the periodic table, we said that if you take metals, you can categorize them into group 1, group 2, and then what are the other majority of metals in the periodic table? What do we call them? Transition metals, all right? So it turns out group 1, group 2 metals are always neutral. Transition metals are not neutral. They tend to be acidic in solution, all right? So for this class, every ionic compound, if it has a cation, it's going to come from group 1 and group 2, all right? Because transition metals tend to be weak acids. Like if you take iron in water, iron cations like iron 3+ will act as a weak acid, all right? So it turns out cations of group 1 and group 2 metals are always neutral. Transition metals have acidic properties, okay? They can be extremely weak, but still they can act as acids. So we're going to kind of, for this level of class, we'll kind of leave out transition metals, and the type of examples you're going to see will come from cations that are group 1, predominantly group 1, like sodium, potassium, rubidium, cesium, and so on, okay? And so these two apply to cations, all right? So when you're studying at home, that's what you have to be able to do. You have to be able to look at acid-base properties of salts. And then now we need to go on to, remember when we dealt with acids, one of the fundamental skills that you need to be able to do is, can you calculate the pH of a strong acid? Can you calculate the pH of a weak acid? Can you calculate the pH of a strong base? Can you calculate the pH of a weak base? Can you calculate the pH of polyprotic acids? Now we got to ask ourselves, can you calculate the pH of a salt? All right? So we're going to take some examples of this. So this is not very complicated. Once you know, you can categorize them. You look at the anions. And if the anions is the conjugate base of a strong acid, it's going to be neutral. If you look at the anion is the conjugate base of a weak acid, it's going to be basic. All right? If you take cations, it turns out that the only example, these examples are very, very few. All right? Cations that are conjugate acids of weak bases, all right? There are very few cations of conjugate acids of weak bases. And the only example that you will encounter is NH4+, all right? So if you go through that list of acids and their conjugate bases that I gave you, and if you look at that list, there are very few examples on that list where your conjugate base, the conjugate acid of a weak base is actually cation. Many of them are neutral, all right? They're not cations, all right? And so the only example that you will encounter most often, and the one that I want you to remember, is NH4+, all right? And then, of course, group 1 cations, all right? So now, let's start taking some examples. So if you look at that worksheet that I've put up on the class website, and it talks about acid-base properties of salts. Okay, so let's take an example where we want to calculate the acid-base properties of salts. What I want to kind of remind you guys is it's the same approach that we've been using all along for every example. So don't get thrown off, all right? So we're given sodium fluoride. Calculate the pH of a 0.0 molar solution of sodium fluoride, okay? So the starting point is to look at the formula of the compound and ask yourself what kind of compound it is. Because it's got sodium, a metal, and fluoride, a nonmetal, and it's a cation and anion combination, you know that this is a salt or ionic compound, all right? And therefore, we know that if you take sodium fluoride, all right, and when this is dissolved in water, it'll immediately form this, all right? So even though sodium fluoride initial concentration was 0.03 molar, the instant it dissolves, remember it dissociates and breaks apart completely. So even though we write the concentration as if the cation and anion are associated together, in reality in water, they have dissociated, all right? So if we start with 0.3 molar of this, can you see that in reality in solution what we have is 0.3 molar of that and 0.3 molar of that. because it's a salt. It's a soluble salt. And if it dissolves in water, even though we write the formula as if they're associated together, in reality, the moment they dissolve in water, the whole structure is disintegrated and it's dissociated. So that means that it's going to have 0.3 molar sodium cations and 0.3 molar fluoride anions. Now if you look at sodium, can everybody see that sodium is group 1, therefore the cation is neutral. If you take the anion, this is F minus. Now if you're not quite sure, you look at your table and you're looking for HF F minus. If you go down, you can see HF F minus. All right? Now, this is important because if you take group 7, which is chlorine, bromine, iodine, and so on, what you notice is fluorine is a weak acid, but chlorine, bromine, iodine are strong acids. All right? So remember that fluorine actually behaves differently than chlorine, bromine, and iodine. They are strong acids, but fluorine is a weak acid. So HF is a weak acid, therefore its conjugate base has to be weak as well. So we know that this is the conjugate base of a weak acid, and therefore it is going to be basic. All right? So now that we know that we have one neutral component, so we're not concerned about that. That's not going to affect the pH of the solution. But the other component is going to affect the pH of the solution. And in that case, we're going to say now the equilibrium that will be established would be F minus in water will give me HF plus OH minus. All right? And since we're writing in the form of the conjugate base, which is basic, we're actually interested in looking at Kb. But do they give us Kb? They give us Ka. So all we have to do is, we know Kb is Kw divided by Ka, which is 1 times 10 to the negative 14 divided by 6.6 times 10 to the negative 4. And that comes out to 1.5 times, let's see, do I have a number for that? 10 to the negative 11. All right, so now we know that this is extremely weak base. It's 10 to the negative 11. All right? So now we have to figure out what is the pH of the solution. If we want to figure out what the pH is, we've got to figure out what the hydroxide ion concentration is. All right? So let me start with the initial. All right? The concentrations are, we have 0.30 molar of F minus. We're not concerned about water. This is going to be 0, 0 to begin with. Okay? So we know the reaction is going to proceed in that direction to establish equilibrium. So if I want to look at the change in terms of molarity, this would be negative X plus X plus X. We're not concerned about water. Okay? Therefore, at equilibrium, if I want to look at the molarity, this would be 0.30 minus X. This would be X, X. All right? So we work tons of problems using this approach. Okay? Now we're looking at Kb. Kb is a really small number, 1.5 times 10 to the negative 11. And we know that equals the HF concentration times the hydroxide ion concentration minus F minus, which is X squared over 0.30 minus X. Since this is 10 to the negative 11, we know this X is going to be extremely small. Can I make an approximation? Yes. All right? So my approximation is going to be 0.30 minus X is going to be 0.30. All right? And therefore, I can go back and say now 1.5 times 10 to the negative 11 equals X squared over 0.30. And therefore, if I solve for X, it comes out to be 2.1 times 10 to the negative 6 molar. Now, quickly check for validity. Is my approximation valid? And that would be 2.1 times 10 to the negative 6 molar. I'm saying that this concentration is really small compared to 0.30 molar. And that comes out to be 7 times 10 to the negative 4. So that is really, really small number. So you can see that our approximation is pretty good. All right? So now that we know our approximation is valid, remember, ultimately, what do I need to calculate? I need to calculate the pH of the solution. All right? So that means we have calculated hydroxide ion concentration, and we know the hydroxide ion concentration equals X, which is 2.1 times 10 to the negative 6 molar. So now I need to calculate pH. So as all of you know, now I need to convert the hydroxide ion concentration to figure out what the hydronium ion concentration is. Or if you have this number on your calculator, you just take the negative log of that, and that will give me pOH, and that comes out to 5.68. And then I know pH is 14 minus 5.68, which gives me 8.32. All right? So remember, this is an extremely weak base, and therefore the pH has to tell me what? That the solution is basic. Does the pH that we calculated indicate that it's a weak base? Yes, the pH comes out to be 8.32. All right? So this is an example of a salt, all right, acting as a weak base. Now, in your worksheet, there is one problem. So I just want to go through. So this is a very qualitative way of looking at it. So I want you to look at this. So in the last 2 minutes, so this is quite a common type of question. So please take time to practice this, and during discussion I'll give you lots of examples as well to practice. So you have the same concentrations of all of these substances. All right? So now you're asked, arrange the following solutions in order of the most acidic to most basic. All right, so we want to rank these. And so it would be a good idea to look at each one of these. So we have KOH, KCl, KCN, NH4Cl, and HCl. All right? So let's look at this. Let's categorize this. Will this be a strong base? Will this be a strong acid? Will this be a weak acid? Weak base. So we've got to rank them first. All right? Now if you take KOH, it's an ionic compound. Its cation is group 1, so you know the cation is going to be neutral. All right? What is the anion? OH minus. Is OH minus a strong base or a weak base? Strong base. All right? So that means this combination, so you're looking at both cations and anions, and so this combination will be a strong base. Now let's look at this one. It's got K plus. All right? So all of these, you know, you can look at the salts first, and this is a salt again. Potassium plus, it's a neutral salt. It's a neutral cation. Does that make sense to everybody? Because it's group 1. Now turn to Cl minus, the counter ion. Cl minus is strong or weak? It's the conjugate base of a strong acid, but a conjugate base of a strong acid is what? Neutral. So that means K plus is neutral, Cl minus is neutral, therefore this will be neutral. Okay? So each component, this will be neutral, and therefore this compound as a whole will be neutral. Now let's turn to this. This is neutral. It's the cation. It's a group 1. So it's a salt. The cation is neutral because it's a group 1 metal. Now let's look at the anion. Anion is Cn minus. So if you're not sure, you don't memorize this stuff. Just you look at the table. HCN is a weak acid. So Cn minus is the conjugate base of a weak acid. The conjugate base of a weak acid is what? Acidic or basic or neutral? Basic. So that means that this is basic. All right? But it's a weak base. All right? So if you combine these, what you end up with is a weak base. All right? Now we turn to this. And in this, if I take NH4 plus, this would be a weak acid because it's the conjugate acid of a weak base. So this would be a weak acid. This is Cl minus, which is the conjugate base of a strong acid. This will be neutral. Therefore, overall, this would be a weak acid. All right? Now, lastly, HCl is an acid. And this we know is what? This is a strong acid. All right? So let's rank this from the strongest acid. Which is the strongest acid? HCl. Now, let's look at this. This is a weak acid, weak base, neutral, strong base. So what comes next? NH4Cl would come next. This is the strongest acid. Next comes this, which is a weak acid. Now we have neutral and the bases. So next comes whatever is neutral, which is KCl. So now we're switching from acids to neutral to now the bases would be, the weak base would be KCN, and then the strongest base would be KOH. So if you look at this, we're ranking this in terms of relative acid strengths, all right? Starting from the strongest acid to the strongest base, okay?